Hello community! We have some brand new research by NVIDIA about a new LLM called Hymba. And yes, it is a combination, a parallelization of Mamba and transformer architecture, and it utilizes something beautiful new, Metatoken, for the new NVIDIA chip hardware architecture. Interested? Well, let's have a look together. Now, normally when we have our LLM, we have the pre-training, we have the fine-tuning, and then we have a DPO alignment. And then we have the inference, so when you send off your prompt and you wait here that the answer is generated for you. Now the new trend, the new improvement is here, like with OpenAI 01, to scale here the test time algorithms for task-specific queries. In my last video here, I showed you that here in the inference run, we use here a LoRa adapter tuning process to optimize here the reasoning capabilities and come close to OpenAI 01. And in this video, we looked here at a solution also in the test time training algorithm that we trained here the policy model of the reinforcement learning and the reward model together to optimize and augment the search base for the Monte Carlo tree search algorithm that we further optimized. Novel ideas for the test time compute. So you see, there's a lot of things happening here in the inference sector, but of course, the policy model and the reward model, they also have to be compatible and coherent structure and have to be trained also here before we start inference. So the complexity of the complete system increases. Yeah, wait for the new idea by NVIDIA, because NVIDIA says, hey, it was a little bit easy, We just had here the transformer architecture with the self-attention, multi-head and everything. Now, let's do this and let's have on our new chips here. Let's do this that we have also the Mamba architecture. So that we have our state space models plus here our transformer architecture. And let's run this in parallel. Now, this is quite a challenge, but hey, I have no access to the new Blackwell chips, but I would love to have access to the new NVIDIA hardware optimization. So here you see if you want the model optimization and the idea optimization. Run it in parallel on the new NVIDIA chip, that would be great. But they noticed and they focus here on smaller models, what we call small language model. Maybe 2 billion free trainable parameters, maybe only 1.x free trainable parameters. So now we encounter a different problem because it has to be small, fast and efficient. So starting now, we talk about sub 2 billion free trainable parameter LLMs or small LLMs. Now the idea by NVIDIA is beautiful because this let's call it LLMs, never mind, are so tiny, You have to provide additional information for a specific task that you're going to ask this system. So for a specific task, you have to prep here your LLM with Metatoken. And Metatoken is something here you put really in front here in your prompt structure, and Metatoken become now here an integral part here of the architecture of the system, and Metatoken will be there for the transformer architecture and also for the Mamba architecture. I told you here task specific. Now in the first run, we're just gonna analyze here the NVIDIA paper in detail, the technical details, and then I tell you the ideas that I have that are just, simple and beautiful to implement. So what we have. Let's say you want to have a benchmark study and you know that you want to do 3-4 benchmark tests yourself. So you integrate now in this Metatoken structure here some domain-specific knowledge or some task-specific knowledge. Let's say here you want then to run this on a benchmark for mathematical reasoning. So you will put a little bit of the best methodologies for a task-specific reasoning knowledge in here, or if you run this here on a test in the domain of medical or medicine or chemistry or physics or mathematics, you will put in the basic domain knowledge that here our little tiny LLMs might not have the capacity to really have been trained on like the big brothers. Great. So now we come back to the original idea here. We have, if we go back to the Big Brother training, we have the pre-training, fine-tuning and DPO alignment. And you know what we do, like Apple is doing this here, for example. you take a general fine-tuned model that has been pre-trained, and now for a photo application or for write a nice summary or do some, I don't know, correction in my video, you do not go and fine-tune here a complete model, but you have adapters. You know, LoRa adapter tuning or quantized LoRa adapter tuning. This is the way that we do it normally. Now, if we take this idea, NVIDIA took this idea and said, great, so whatever is now a specific task, a specific benchmark, a specific domain that we want to have the test run, of course, and show that this is the best model, of course, we provide now some knowledge here in this MetaToken sector here. And of course, and the beauty is we integrate this in one architecture. Remember, they have to do the pre-training, they have to do the fine-tuning, they have to do any alignment because we have a complete new structure running on a complete new NVIDIA chip, Blackwell, whatever it is. So they have to do everything. And now they say, what is the best way to optimize this since we have to do the pre-training? And now they build a model and they call this model HYMBA or HYMBA, whatever it is. It is simply kind of a hybrid system of a transformer and a Mamba system. But there is much more to it. And this is so beautiful, and this is what I would like to focus on, the Metatoken. Because they are then embedded, they are an embedded data structure given here the vector space that the transformer will act, plus we will use Metatoken also for the state space model, and you know what, for the initialization of the state space model with Mamba architecture. You could now theoretically ask, and I ask myself, but why do we need a Mamba? Mamba is not that powerful, and we know ways how to reduce the quadratic complexity of the transformer architecture, because if you are a subscriber of this beautiful channel of mine, you know, a year ago I showed you here the ring attention by Google or by Infinity here. If you have here 1 million context length, how you do this, that you're not getting crushed here by the quadratic complexity. So we do have solution. But remember, this here must be for tiny little LLMs, maybe on your phone, maybe on your watch. So we don't have the infrastructure, we don't have the power. And of course, for Mamba, I don't know if you've seen it, but I have a beautiful video. If Mamba AI, I looked here particularly at the S6 model, is it better than transformer? And then we coded here together a hybrid Mamba transformer already. But remember, this hybrid had some problems. You remember that while the traditional transformer faced here the quadratic computational cost with the complexity and the high memory requirements, while our state space model, despite their non-quadratic computational efficiency, they struggle with memory recall task. And we tried the hybrid architecture to bridge this gap, but we faced bottlenecks due to the sequential nature of the layer integration. And now NVIDIA is coming and saying, yeah, I run this on my new chips in parallel. So hybrid, well, hybrid with, you have to understand what is hybrid. Hybrid means parallel. If you want to see the test and how we do the supervised fine-tuning and the DPO alignment, here's the video for you. And if you want to go beyond Mamba S6 models and have a little bit of mathematics and theoretical physics, we will go to vector field. This is the next step of evolution beyond Mamba. So if you're interested in this, these are the videos for you. But let's stay simple. No? NVIDIA wants to be here simple every day. Every user should have multiple agents here. So simple idea Mamba. We don't build here complex ring attention mechanisms. So we use a simple Mamba system for if you want a long-term memory. Now you might look at this and say, wait, I could have the theoretical possibility of in-context learning. So why does NVIDIA not go here for the new hardware acceleration of the new chip with in-context learning? And yes, I have some beautiful videos for you, how in-context learning outperforms fine-tuning and rack system. And you don't need any more fine-tuning because we have something like I called in-context learning plus, and I explained this in detail here to you. Not to talk here about recurrent system for especially designed for long context, but remember, we have to be simple, down to earth. So this idea of Metatoken, it's so beautiful. Let's do a definition. Metatoken, according to NVIDIA, are initialized as a trainable embedding structure and are optimized alongside the rest of the model parameters during the training. starting from the pre-training, because they have to build everything new from scratch. And this MetaToken acts as an additional layer of memory or context that help the model, since it's so tiny, to process here the sequences more effectively if I have a complex question to my AI system on an NVIDIA chip. So during the training, the MetaTokens interact now with the input sequence of my personal query, and this influences now the attention operator in the transformer architecture plus the state space transitions here in our Mamba structure. So the values of the MetaToken, the embedded structure, now are adjusted to minimize in a complete system architecture, to minimize the loss function across the training task, thereby embedding here critical contextual knowledge about the domain, about how to do reasoning, or task-specific patterns. So this is a beautiful idea because the LLM is so small. We add for our query that I ask, for example, the system chooses here the MetaToken as an additional, if you want, shell, an additional information body that is provided to the LLM together with my query. And everything is trained together. So those MetaTokens encode general knowledge that is not inherent in the parametric knowledge of our LLM. As I told you, math context or legal reasoning, you have to have certain templates to follow. So all of this would be in the MetaToken structure because the LLMs are so tiny. If you want, you can see this as a learned cache, or as a, if you go with Mamba, as a state initialization procedure, thereby improving the memory efficiency and the recall capabilities of the complete system. Now, we have alternatives, and NVIDIA, I'm sure they did a lot of beautiful tests on their beautiful new chip architecture. They could go with in-context learning, or they could have optimized prompt engineering, especially for small LLMs, but they decided to go with MetaToken. And this makes it so interesting that MetaToken, what a brilliant idea. However, if you do this now for a task, you have to train it a complete system. You have to do the pre-training, the fine-tuning, everything. And you might say, okay, listen, for 1.2, sub 2 billion, this is a little tiny nothing. I can do this in an hour, no? Yeah, I know. But yeah, let's start easy. So we have this, so we know what we want to use this model for, and we train the complete new model with the transformer and the Mamba parallel structure here for a specific task. Great. But imagine thinking about my last two videos about here the test time algorithm for a specific task. We could have theoretically, for a very specific task in the inference round, the possibility to choose, given my specific task, the coherent MetaToken for the task optimization. So we could use this using knowledge graph or specific embeddings to map queries or to domains, selecting here all the relevant MetaToken for task-specific queries. No? Or if I go crazy, maybe I train here a lightweight query condition generator to dynamically create synthetic MetaToken for unseen tasks, like we did here when we trained our LoRa adapter for this other test time algorithm. No? You see, so many ideas given just here, a beautiful new idea. So, MetaTokens compensate, if you want, for the LLM size limitation, less than sub 2B, by providing here essential contextual guidance or some task-specific initialization for the Mamba system. They are learned embeddings. You have to run the complete process, so they are integral part that encode domain-specific information, legal, scientific, mathematical, whatever you are working with. But they can also be task-specific because, as I told you, you can have domain context like quantum mechanics, you have the basic principle of physics. Or if you want to go with structural, like how to write a mathematical proof, just learn it to proof format. Or you have some knowledge relevant. How to best summarize here a research paper? What are the best methodologies to do that? It will not be inherent a parametric knowledge of the LLM because it's too small, less than 2 billion free-trainable parameter, but you put it in the metatokens. So by acting now as anchors for the attention mechanism in our transformer, or as anchors for the state space update in our Mamba structure, we both run both in parallel. I will tell you how we will come together. Those metatokens ensure that our small language model focus on the relevant aspects of the input with our guidance for a specific task. It's a gorgeous new idea. This is the third video, if you want, here on test time optimization compute adaptation. So study here, 2024, November 22nd, HYMBA, a hybrid head architecture. Looks so innocent, but my goodness, if you read the paper, it's great. And of course, I give you the result. This model here by NVIDIA on their super chip, I call it. I have no access to those chips. It surpasses here and outperforms even the Llama 3.2 3 billion. So a 1.5 billion outperforms a system that is double as mighty as here the base model. Impressive. You find this on Hugging Face, but I don't know about your hardware configuration. I don't have access to all of those chips. And of course, maybe they are downward compatible to old chips, but I think the real power will come with, I call it the next generation. Maybe you already have access to these models. So, short summary, what is the main point? This new hybrid model is a parallel model. And it optimizes here these new metatokens jointly in the transformer architecture with the model weight during the pre-training stage. And the metatoken is compatible here with the sliding video attention heads and those mechanisms that we have in the state space models in our Mamba structure, because it converts here the metatoken also, because we have to bring transformer and Mamba together in the parallelization world. It converts the metatoken into key value cache initialization during the inference run without modifying here the architecture, because believe me, the architecture is complex enough. So nice, no? These new chips and these new models, I like it. But you know what? There's something interesting in the technical paper. If you make a deep dive in the paper, please read it, even if you don't like here hardware acceleration. But there's something nice. Have a look here. The token and the distribution of the attention scores, and we will look here at the entropy calculation, and this will provide us with some information. Okay, if we go now on a token level, we have here matrix, here our metatokens, and then normally we have our indicator that our human sentences start, and we have specific tokens like the beginning of sentence token. And this is used in the classical transformer model and similar architecture. This is just an indicator. But unfortunately, there's something happening. Because in the self-attention mechanism or multi-head, you can see, and now they investigated the Llama 3.2 3 billion free-trainable parameter model, that if you look how much attention is the complete system paying just to the beginning of sentence token that has no content except it tells the system, hey, look, I'm here. Here the first sentence of this human starts. Look at the attention scores. 56% of the complete attention span goes to one single token. This is crazy. Sorry. So, be more precise. Llama 3.2 3B, more than 50% of the attention is focused here on a single, just indicating that something will start here, token, beginning of sequence, token here of our sentences. Yeah, sequence, sorry. Sentences is the human word, but beginning of sequence. Great. Now, interestingly, with this metatoken, we have added benefits. This is so beautiful, because this helps us to offload here this attention burden, this over-focus here on special tokens, on specific tokens that we have here. So by redirecting now the focus from the beginning of sequence to the metatokens that are before, the model can now distribute the attention calculation much more meaningful across the complete sequence. And what they observed, NVIDIA, not me, is when the prompts are from different domains, let's say an article about mathematics or code or whatever you have, different metatokens are activated now in the inference run. So this suggests that different metatokens encapsulated now in their embedding different world knowledge, which makes sense. And this different world knowledge that is encoded in our metatoken can now be leveraged to guide the attention mechanism to focus more on the relevant information. And this is exactly what we want. If I have a simple query in the inference run, and I say, hey, explain this mathematical formula to me, I want that here in the attention mechanism, the system understands that it's about mathematics, that mathematics has some formalism if you want, and I want to have here an explanation given here the mathematical standards. Or if you do code, you don't want that you switch between, I don't know, 10 different computer languages, but you have it here in a coherent form. So whatever is there in the knowledge in the metatoken, hey, sexy new thing. There's another thing, if you calculate now the attention map entropy, if you are a little bit into theoretical physics, you know we can use in computer science also our insights from the theoretical physics side. And they calculated, and this is really amazing from NVIDIA, wow, they calculated here the attention map entropy for each single layer and the heads. So remember, we have a parallel structure. Here we have the attention heads from our transform architecture, and here we have the SSM heads from our Mamba structure. And you see here with and without the metatokens. And in the lighter orange, if you want, you see here with the metatoken. And this reflects exactly what we want. So with the transformer, this works beautifully. Look, everything is perfect. Just here, typically with the Mamba, we have two problem areas, but never mind. Normally, with the metatoken here, the darker blue, is here much smaller the entropy here, given all the different layers that were analyzed. So, yeah, definition, what is the attention map entropy? It simply reflects the distribution of the attention scores across all the different tokens, where the lower entropy indicates here a stronger retrieval effect as the attention scores are concentrated here around a smaller subset of tokens, a higher localization of the knowledge. And this is what we want. So this is a beautiful indication that this thing is working. And it makes sense if you think about the mechanism yourself. Great. So up until now, we talked about we have a parallel structure, transformer and Mamba. Now we have to bring them together because, you know, there's now the beautiful problem of key value cache in transformers and in Mamba system and how to run them in parallel and then optimize here the cache optimization. We start easy. Key value cache in transformers. You know that each attention head computes here the key and the values for the token in the input sequence, and during the inference run, those key and the values are stored here in our key value cache to avoid recomputation every time. So this is especially important for tasks that involve here longer context windows. So what we have sharing that is happening here of the key value caches, and this can reduce our memory usage and our computational overhead of our AI system, and this is beautiful, this is what we want. Now, we have two possibilities, no? We can use the same key value cache shared across multiple layers of the model, or the same key value cache is shared across multiple attention heads within the same layer. Now, this is now kind of an optimization structure if you build your own transformer architecture. So you have those two options. And, which is logic, by sharing the key value cache, the redundant storage is eliminated without a significant performance loss. And NVIDIA gives us here data, and they say here we can reduce the memory footprint significantly if we do this. In this HYMBA, we have up to a 3.8 times reduction in the memory. However, please notice there's also here a dark side to this, because whenever we do a simplification, we lose precision. So layers may lose the ability to independently adjust their key value mapping for different specific subtasks or specific input sequences. So this means, you remember from the general idea of a transform architecture, different attention heads were looking at different semantic or syntactic or whatever properties of our sequence, of our sentence. So this attention head in a layer often focus here on different relationship in the data we have. Syntactic, semantic patterns, and whatever. Now, sharing between the head, we risk now to reduce the model's fine ability to capture these real small, subtle differences, these diverse features. But, of course, we get here reduced memory and faster processing. And now this is now also an optimization process by NVIDIA, and they tell us that their HYMBA primarily uses here a sliding video intention, of course, in most layers, which reduces here also the size here further of the key value caches by focusing even more on the local content here in the sliding window rather than the global content. And I have a specific video on the sliding window attention mechanism. My goodness, I need a cup of coffee. So now I was a little bit amazed when I read that this HYMBA new model by NVIDIA, of course, this is only a prototype, and the first day, it was published today, so it's the first day. If they talk about long context, they say, yeah, we can handle up to 8,000 token. Now, today's standard 8K token is great for a parallelized transformer Mamba structure with shared values, but in the general world, 8K is not really that. So, okay, so we have to begin somewhere. We begin with 8K. Great. I wanted to investigate the role of Mamba here in this HYMBA, and I said, but why? Is it really so much easier when we have this simple system? Is Mamba really contributing to this simplification of the architecture for the hardware acceleration? But it seems that NVIDIA is going here with this step and not using here a more complicated mathematical algorithm. Mamba, if you want, summarizes here for this HYMBA system here the global context more efficiently without here the need to process here the expensive full sequence attention in the transformer architecture. Therefore, this task is now here given to Mamba. And Mamba also acts like a fading memory, so retaining here critical global features, thereby also reducing here the memory need for our transformer. Okay. Then NVIDIA tells us, and I can't validate this, I have no access to those chips, is designed here to leverage here the linear algebra operation on the chip in, let's say, in a better way. And this aligns well with the GPU chips from NVIDIA or the tensor processing units by Google. Although I can imagine that Google with their tensor processing unit might have a more focus on the transformer architecture, but whatever it is. So NVIDIA tells us here, HYMBA benefits from this hardware compatibility with these beautiful new chips, whatever, achieving faster processing speeds and higher throughput, even when processing 8K sequences. Great. And now let's come here to my crazy idea at the end of the video. And I thought, hey, if this is something, I mean, we have to have the chips and we have to have the software that is compatible with this hardware, and then we run the optimization. But if you think a little bit in the future, could we not integrate here this new Metatoken with the in-context learning that we know so much about? Because think about it. The Metatoken could represent here the knowledge about a domain, like the mathematical reasoning procedures or the legal analysis templates that we have to run through, helping the model, the new LLM, better interpret here the in-context learning example that we will provide in the input prompt. So this is interesting. Can we take this idea that NVIDIA developed here for this really tiny sub 2 billion free trainable parameters language model and not use it here in the normal large language model world? I think this is an interesting experiment, but unfortunately I don't have access to the new chip architectures. So Metatokens, remember, are a model internal fixed embedding structure. They are in the pre-training, but there are ways here to find maybe an coherent adaptation to this, because we are working here in a mathematical vector stores, and I have already 2 further ideas for this, whereas our in-context learning examples are now external user-provided inputs. And I think this, although they are different, this would provide a beautiful, beneficial relation, no? Because we could instruct the model in our test time training on the specific domain knowledge that we would provide in the metatokens, and we would have an additional in-context learning examples, whatever we have in our databases, whatever we know, than in our prompt structure for the prompt optimization. So you see the automatic prompt optimization by this OpenAI and Perplexity, they will come to their limits with this new integration. I think they could complement each other, but of course now the question is, we have to run the test, what about the costs? Because I can imagine now this is going to be really expensive, because if you look here at OpenAI, this O1, sometimes we have to wait 90 seconds, 120 seconds for an answer. And now imagine we have a complete new hardware architecture on the chip that we run here, the Mamba architecture also. And also we can share some key value cache, and of course we can optimize this, but I think this is gonna be a real costly exercise. But you know, we're thinking here about new ideas, new models, new hardware, new architectures for the future. So I think this is something we should investigate whenever chips will become available for us. And there you have it. This is the end of my video. I hope you had some new ideas. I could show you some brand new methodologies, some new models that you could try out, especially with the new infrastructure by NVIDIA. So you see, talking about walls or whatever, every day we have some brand new ideas. We have some fascinating implementation of those ideas. Those companies build complete new models now with parallel transformer Mamba architectures. And seemingly they outperform everything that we know about. They outperform our old AI system that were just published 3 days ago. So it would be great if you subscribe. We will see each other in my next video.